Oh yeah, let's try this again. Load them up here. Go to this fallstad.com site, which brings up this little Java applet. Delete this stock stuff that comes out with it. Let's see here. Oh, got to import my reference file. Import, close. Okay, there it is. Now, block diagram of POCASA. You got the signal generator going on over here. You got a pulse generator here. The X-axis input to the ADC over here. The Y-axis input to the ADC down here. Okay. I'll just run left to right. The pulse generator, or the signal generator here, AD9833 direct digital synthesis chip. It puts out a 0 to about 12 megahertz signal, depending on your crystal. And the sine wave, or the wave output, runs from 0 to 0.65 volts. Goes through this op amp here. About a 7.8x gain. Going to have a digital pot right here, which is basically attenuating the signal to this buffer. AC coupled this 10K resistor, which forms part of the gain loop for this. On the offset, plus 2.7 volts, minus 2.7 volts. Why 2.7? Because I've already got them handy on my circuit board. Little voltage divider here, buffered resistor, again part of this gain circuit, inverting amplifier. With what's the gain on that? I forget. Oh, 6.2. And the output is here. So let's go ahead and view that in the quote-unquote scope down here. Speed this up a little bit so we can see it. And I gotta speed up the simulation. Takes a little bit of configuring to get this to work right. Okay. Slow that down just a tad. This is the signal that's right up here going into the source resistance. Plus 10.5, minus 10.43. Let me even that out here. So I get plus and minus equal signals. Now it's going to get all goofy here. Don't worry about it. Come on. Cut me some slack here, will you? There we go, 10.05, 10.05. Close enough. So what this will do, this will provide a signal for the source resistance right here, which right now I've got this set for, it's a 10K pot. We'll jack that up to 100 just to make it easier for later. Source resistance is right here. Dial that in. My device under test goes right here, which right now it's a 100 ohm resistor. I pick off my X axis here, and the X and the Y are the same thing, so I'm only going to describe the X. I buffer the X here for high impedance input, so I don't put any kind of load on the device under test side of things. Divide the voltage down by a little bit, assuming a 15 volt input, so I don't max anything out. This is my input to this buffer amplifier here. This is my offset. Same thing that's going on over here, except it's DC coupled to the final amplifier. And this one here's got a gain of 180, which is quite a bit, but it'll be alright. And there's a load resistor here. So we can look at the X output and the Y output. Now I'm going to have to speed both of those up to match. I don't know who made this program, this Java app, but I like it. One more time should do it. There. Shut off the current, show the negative peak, shut off the current, show the negative peak. There we go. Now in my case, I have to not put any negative voltage into the ADC, so I got to dial. Okay, that's the wrong way. Just got to set a few parameters here. Got to go between 0 to 3.3 volts. in order to keep from smoking the ADCs. So that's good enough. Let's turn up a little bit more gain on the Y here. Offset it a little bit up. And there'll be a monitor on this side of things, or actually up here, and I'll be monitoring these to see if either of them go negative, and the software automatically adjusts the offsets and the gains to provide the maximum range. I don't know if you can call it that. I don't know if that's the right term, but you get it as close to 3.3 up here and as close to 0 down here without going over, just like the Price is Right. Yeah. You see now we got 3.1 here, 32 or 38 millivolts. So I can dial it up like 1 or 2 more. No, I can't. Okay, Y offset back down. Turn the gain back down. Okay, looks like in this case, I'm only going to get 38 millivolts up to 3.1. 3.1 minus, we'll call it 39. 3.061 volts out of 3.3 on a 12-bit ADC is going to give me 3,799 counts. That's plenty to work with. Let me just mess with the X gain here a little bit. Okay, that's too much. So I'm going to get about 3,800 counts on the Y side. On the X side, I'm going to get 0.68 minus 0.464. 3 times 4,096. I get 2,750 counts. And that's plenty. I mean, 3,800 pixels by 2,750 pixels is plenty to see what's going on. And I'm going to ignore the pulse generator side of things for now, because with this simulator it just doesn't quite work right. So anyways, I'm going to go ahead and view the device under test in the scope. Again, I got to speed this up a little bit. Only because the settings aren't saved, because they between runs they change all the time. So I'm going to plot show V versus I. I'm going to not show the current. Show negative peak value, and I'm going to maximum scale that. So a 500 ohm source resistance, which is R1, the right side of the resistor basically, 500 ohms versus 100 ohm, and this doesn't quite work right, because if you scale it, it auto scales in both X and Y, and it just doesn't show right. But it'll be a slanted line like that. If I get rid of that and throw a capacitor in there, view that in the scope, then change all these goofy settings. It's got to steady out. It's got to get to a steady state here. And again, here's where the scaling gets a little goofy. You see it rescaling itself there. And you see how it's overshooting and kind of undershooting, and that's the AC coupling going on. You just speed it up here. It's going to get a little choppy, but it'll smooth out. That is what my scan will look like on the scope, or on my display anyways. 10 microfarad capacitor will look like that. If I were to change that to, say, a 0.1 microfarad capacitor, and you see how it didn't rescale itself. So that's good. That's 0.1. A 0.1 looks markedly different than a 10 microfarad capacitor. See, you know, it's getting all this stupid scaling stuff. Wish I could lock the scaling down, but I can't. Well, yeah, I guess I can. Because it won't scale itself down, it'll only scale itself up to fit. So that's what a 10 microfarad capacitor will look like compared to a, let's just do a 1 microfarad capacitor. Okay, it didn't rescale. Good. Okay, 1 microfarad is going to look like that. And you see my Y out here has gone all goofy here. So even though it looks good here, I'd have to rescale my digital pots, my y-axis, my y gain, and my y offset. So let me dial those back just a little bit here so I don't exceed my maximum values. Okay, that's too much. We might be able to offset that up one. Nope. And if you look at it just right, you'll see that there's a definite phase shift between here and here, causing the X and the Y. Basically, a circle is a sine, cosine differentiate, or different by, or offset from each other by 90 degrees. A perfect circle is offset by 90 degrees. And you can see there's a definite phase shift going on here. Let's see if I can stop it at just the right point. Yeah, there's a definite phase shift. And again, that might not be a nice oval like it is right there. It might actually be a tall, slim one. It's just that the way this software scales the output, it looks weird. So anyways, let it go ahead and run. Now we'll go ahead and get rid of this capacitor, and we're going to put a diode in there. Go show it in the scope. V over I, no current. There you go. Now I got to rescale my gains again. Oop, too far. Turn up the gain just a little bit. Turn it down. And this works a lot better than the real circuit because there's only 100 steps over here in these horizontal scroll, not horizontal scroll bars. Yeah, horizontal scroll bars. In my circuit, there's actually a 200 or an 8-bit digital pot, so there's 256 steps, and I can use a 10-bit digital pot with 1024 steps. And anyways, that diode will look like that on this scale, on my output. It'll look like basically, and it goes up like that, and it goes up like that. See if I can max scale that. Yeah, that looks better. That's what it will look like. So in any combination, I don't know if I can use an inductor or not. Well, you know what I should do? I should put a cap in there and change the frequency. Oops. Do that in the scope. V over I. Max scale. I'm going to change this 400 hertz to 1 kilohertz. Here you see it got more vertical because a capacitor at a higher frequency acts more like a short than an open. And if I increase it even more, let's see, we'll go up to 10 kilohertz. Again, this scale's weird. So let me reset that a little bit. Okay, dial up my X and my Y offset. Dial in some gain here. Dial in a whole bunch of gain. And this is all a simulation, so it works. Let's slow that down just a little bit. Now 10 kilohertz, it's even more of a short than an open. A short is a vertical line, and open is a horizontal line. So you take any one of those, any combination of those, you get a circle with a tail on it. Kind of looks like a golf club. That would be a diode in. Let me think. A diode in parallel with the capacitor would kind of look like a golf club. So if you know your circuit's a diode in parallel with a capacitor and you get a circle, well, your diode is opened. If you got a diode in parallel with a capacitor and you got a slanted line, then you know the diode is shorted, because it's shorted across capacitor, ain't doing any good, and your diode is conducting equally well in both directions, so diode's not any good. I just said that, yeah. But your capacitor isn't even in the circuit because of the diode. And an inductor is almost like a capacitor, except it flattens out the top and the sides due to saturation and, what's the other word for it? I forget. Doesn't matter. Anyways, this is the basic circuit. Digital pot, digital pot, digital pot, digital, digital, digital. 4 op amps per section. You know what? Let's go ahead and throw in the pulse generator for the hell of it. And the source resistance, there's going to be a 8-channel analog multiplexing switch selecting between 8 different resistors. Only because I can't find a digital pot that'll handle the current. But I can find digital switches that'll handle the current. And same thing in the device under test. It's just going to be basically a fan out. Couple of digital switches selecting the upper side to the test points, the signal going into the test points, and applying a ground to all those test points. And as well, the pulse generator going to any one of those test points. Maybe you got a transistor in here, you apply the pulse generator to the base, and you put the emitter up there and the collector down here, and pulse the base on and off, and you watch your signal go from a short to a chair to a open or what have you. Let's go ahead and get rid of this. I got 25 hertz going in there. Let's dial it up to 400 so we can see it easier. And we're going to look at the output here. Speed it up a little. I'm going to turn it up here a little bit. Alright. And it's my pulse gen level. It's either going to be positive or negative. Right now I got the positive selected. And again, digital switches here to select from positive to negative. But if I select them both, basically shorts it out. Nothing going on out here. Turn the level up and down, nothing going on. So I'm going to shut off. Everything positive. I got to turn this down just a little bit. Or at least find my 15 volt point, because the op amps are going to be driven off of 15 volts. Okay, there's my positive, 0 to 14.97 volts. Shut that off. Zero's out. Negative there. And it will be 0 to negative 14.97 volts. And I realize this is a simulation, so nothing's going to be perfect, but it'll be close enough. Same thing here. The signal generator comes from MCU I/O pin because it doesn't need to be nearly fast as the signal generator up here. Inverting op amp, gain of 3. And same thing, tapped off there. It goes through a non-inverting op amp, gain of 3. Selected by the switches, current limiting resistors to the attenuator, to a buffer, a little 2.2 amplifier, or a gain of 2.2 amplification there, back to the output. And again, I shut that off, I turn that on, now it's positive, turn that off, turn that on, now it's a negative wave. And you'd use a negative wave on, like a P-channel MOSFET, PNP transistor. Use the positive wave on a N-channel MOSFET, NPN transistor, what have you. And it doesn't have to be 50% duty cycle either. Maybe it's only 10. And because that's coming off an I/O pin off the MCU, you can program whatever you want. It doesn't matter. Let's see, anything else here? And this is the perfect circuit in a perfect day with perfect op amps. I don't expect it to go this way. There's going to be some things that got to be worked out, but That's basics. This and these two are the same, except that this is AC coupled. These two are resistively coupled. That's it.